Now, let's try to apply what we have mentioned in the previous video to draw the free body diagram for a few cases that we have here. So we have case 1, horizontal surface, case 2, inclined plane, and case 3, hanging object. So we'll be following the steps that we mentioned in the previous video. If you're not sure what do I mean by the steps, please refer to the previous video where we discussed the step that you need to follow in order to draw a free body diagram systematically. So now let's look at the first situation here. The first step that you should follow is you should determine your object of interest. Well, for this situation, it's quite straightforward. Our object of interest will be this thing over here, which I think it's a sleigh, the one that Santa Claus rides on. So this sleigh will be our object of interest. So what we do after we determine the object of interest is we use a dot to represent the object of interest. So this dot that I draw over here will be representing the sleigh over here. Okay, step 2 will be to think about how the axis should be oriented. Well, if you look at the case over here, we have a surface where the sleigh is on top. So if you think about how the sleigh can move, it should move on the smooth surface, right? Something like this. So you should dedicate one of the axes to be in this direction. So in this case, this will be similar to the conventional x and y axis that we usually see. Nothing fancy, no rotation at all. Okay, yeah, y over here. So you have your x and y. So once you have labeled axis, that's the second part done. But if you notice here, I put my axis using dotted lines because the axis is not my main focus over here. My focus will be the forces that are labeled in this free body diagram. The dotted lines here, the two axes, the x and y axis, is here just to help us to resolve the forces that we label on the free body diagram later. So it's not our focus, so we just do it using dotted lines, and we should keep our x and y very small. We just write it just to remind ourselves where is the x-axis, where is the y-axis. It's not the main focus here. Okay. The third step will be to ask ourselves the 5 questions. So we are going to ask the 5 questions to ourselves now. So this object of interest here, does it have mass or not? Yes, this is a sleigh. A sleigh is made of wood, so wood have mass, yeah. So of course, because it has mass, then the ground is below it, so the earth is beneath it. So in that case, you should expect a weight, and the weight should be pointing downwards. So this is your first force that you draw. Okay, any force that you draw, any vector that represents force that you draw in the free body diagram, you should start by going out from the dot. Any force arrow should be coming out from the dot. Okay, so in this case, coming out from the dot, pointing downwards. That is our weight. Second question, is this attached to any strings, ropes, or cables? Well, if you look at this situation here, this sleigh over here, it's not tied to any ropes or strings or cable explicitly. So in this case, we should, because there's no ropes, there's no strings, there's no cables, you can say that there's no tension being exerted on this sleigh over here. Okay, so second question being asked, done. Third question will be, is there any force being applied or being mentioned explicitly? Well, there is. They even label it using a big fat red arrow over here, and they label it with the name P over here. So they give this force a special name, P, and they say this force is at angle 30 degrees above the horizontal or above the ground. Okay, so since I have identified there's a force being mentioned explicitly, so that will be our external force, so we should label it in our free body diagram. So it says it's 30 degrees. So we'll draw exactly the same thing coming out from the dot at 30 degrees above the x-axis. So we'll label this as 30 degrees. Then we will label this force as P. Okay, you might think that, oh, isn't this external force? Why didn't we label it as F? Well, if they give you a special name, then you can just follow the special name that they assign to this force over here. Okay, so fourth question, any contact with any other thing? Well, this sleigh, is it in contact with anything? Well, yes, it is in contact with the surface, right? The ground or the floor, as you call it. So since it is in contact with something, then you should expect there's a normal force. And since the sleigh is only in contact with one surface, which is the floor, you should expect only one normal force in this free body diagram. So we learned that for normal force, the direction of the normal force should always be perpendicular to the surface, because the word normal means perpendicular. just like what you learned in maths. So you should expect your normal force to be in a line with this dotted line over here. But whether it's pointing this way or it's pointing this way, you have to think of the word push. Okay, how does the floor push the sleigh? Okay, if the floor is supporting the sleigh like this, then if the floor wants to push the sleigh, it can only push like this, right? If it exert a force downwards, that it's a pull already. The floor will be pulling the sleigh already. But now no, when we talk about normal force, we talk about push. So this sleigh here, because it is in contact with the surface want to push on the sleigh. So the push will be this way. Okay, so you should expect your normal force to be pointing upwards, which is the case over here. So as I label, coming out from the dot, coming out like this. Okay, I should be exactly on the dotted line because it's coming out perpendicular to the surface, right? And this y-axis is perpendicular to the surface. So maybe I should draw it again, just be very clear. Should be coming out from here. Here I label it as N. Okay, so this will be normal force, the only normal force in this situation. Last question, is it a rough surface? Well, they explicitly mention it's a smooth surface. So if you see words like smooth or frictionless, then it means there is no friction being exerted in this situation. So no, there's no friction over here. So once you have asked yourself the 5 questions and you have identified and drawn, labeled all the forces, then that's it. You are done with your free body diagram for case 1 over here. Okay, so case 1 here only has weight, an external force, and a normal force. And we label the angle if we know the angle. Okay, so now let's move on to the second situation, which is an inclined plane. So over here you have 3 objects. You have your table. Then on the table you place a triangular object, something like a triangular block. Then on top of the triangular block you place something like a parcel. Okay, so you have 3 objects over here. So which one will be your object of interest? The first question, which one is your object of interest? Well, we rarely are interested with the table, okay? Just like we are rarely interested with the ground. And we are rarely interested with the triangular block because that's just to provide us with a slanted surface for the parcel to move. So in that case, our object of interest will be the parcel. So we represent the parcel with a dot. Okay, now that we have drawn a dot to represent the parcel, let's move on to the next question where we should think about how the axis should be oriented. Well, this parcel here, it's placed on a rough triangular block. So you should expect if the parcel can move, then it should be moving around this dimension, right? Any motion should be along the inclined surface over here. So you should dedicate one of the axes which is parallel to the inclined surface over here. So one axis should be here, then one will be perpendicular to the inclined surface. So let's draw it out. One of it will be parallel to the inclined surface, which we usually label it as X. Another one will be perpendicular to the inclined surface, which we label it as Y. Okay, now that we have labeled our axis, let's move on to the third step where we ask ourselves the 5 questions. First question, does this parcel here has mass? Well, this parcel here is made of stuff like papers and cardboards and stuff. So you should expect there's mass, okay? So it's made of something, it should have mass. Then is the earth below? Yes, the earth is beneath it. So you should expect weight. Okay, this is the gravitational force exerted by the earth on the parcel. Next question, is there any strings or ropes or cables attached to this parcel? Well, do you see any ropes around the parcel? No, so that means there's no tension being exerted on this parcel over here. Third question, is there any force being mentioned or being applied can you see any force being mentioned explicitly over here? Well, no, you can't see any force being labeled over here. Then there's no words to describe as external force. So in that case, there's no external force in this situation. Fourth question, is the parcel in contact with any other thing or any other surface? In this case, yes, the parcel is touching something. The parcel is touching the triangular block. And since it is touching something, you should expect a normal force. And since the parcel is touching only one thing, there should be only one normal force. So what is the direction of the normal force? Well, normal means perpendicular, so you should expect the normal force to be along this line over here. But whether it's pointing upwards or pointing this way, you should think of the word push. So the rough triangular block is the one that pushed the parcel. Okay, it's exerted by the rough triangular block on the object of interest. So the triangular block is holding the parcel. So the triangular block, if they want to push the parcel, it has to push this way. If this way, you'll be pulling already, which is against what we say, one push. So the normal force should be in this direction. So you should expect your normal force to be pointing in this direction over here. And this direction here is of course perpendicular to the inclined surface over here. So you should draw your normal force coming out from the dot perpendicular to the surface, therefore along the y-axis. And I'll label this as the normal force. Okay, so this is the fourth question being asked, and now we have labeled it down. So the fifth question, is this a rough surface? Well, it's very clear that this is a rough surface because they write the word rough. Okay, so since it's a rough surface, usually in question they will say rough, or they will say a coarse surface, or made of sand, or a very sandpaper, something like that. They'll do something to indicate that it's rough. Okay, so since it's rough, you should expect friction, and we learned that there's two types of friction, whether it's kinetic friction for things that is sliding across the surface, or static friction for things that are not sliding across the surface. In this case, they didn't mention really clearly whether the object is at rest or the object is actually sliding down the rectangular block. And since we don't know, you shouldn't assume anything. So what can you do is just call it a friction instead of calling it a kinetic or static friction. Just call it generally, call it friction. But what direction? Well, you assume this rough surface here is a smooth surface. If you change it, if you imagine it to be a smooth surface, then where will the parcel move? Or where will the parcel slide towards? The parcel will slide towards, slide downwards, right? In this case, the opposite direction, which is upwards, up along the slope. This direction here will be the direction of the friction, because it's opposite the direction where the object tends to slide if the surface is smooth. If the surface is smooth, it's this way, opposite that way. Okay, so let's draw it out. So it's along the surface, of course, because it's exerted by the rough surface. So oops, I should come out from the dot. Then I should label this as friction. Okay, I don't label the subscript S or subscript K because I don't know it's kinetic or static friction. So I have asked myself the 5 questions, and this is all that I get. And that means what? That means I am done with my free body diagram. So this is the free body diagram for case 2 over here. Okay, now I move on to case 3. Case 3 is a bit more interesting because that's where you get some of the interesting ideas of what is actually object of interest and whether things can be messless or not. Okay, but let's move on. Case 3 over here is a hanging object. So you have a ceiling. So you you have 2 ropes over here, knotted. You tie a knot here, then connected by a string here. Then you hang a mass M over here. So this is a situation. Again, we have to determine our object of interest. Well, you being doing the free body diagram for the first 2 cases, you straightforward think, okay, of course, this block over here will be the object of interest. Okay, so let's use a dot to represent this mass over here. So this dot over here is representing the mass M over here. Now let's try to move on to the next step. The next step will be think about the axis. So if you think about this situation here, it's more likely that this block here will either move up or down, right? Imagine if you cut the string, then the block will be moving downwards. Yeah, sometimes it's uncertain. In this case, it's a bit uncertain, but it's more likely that it's able to move in this direction. So in that case, you place our axis, one along this dimension, then another one perpendicular to it. So you label one of it as X, label one of it as Y. Okay, now we have done the second step. Ask ourselves the 5 question, which is the third step. So does this object here, this mass M over here, does it have mass? Yes, they say mass M already. Okay, then is the earth beneath? Well, if the ceiling is up top, then the ground should be below. So you should expect a mass. Should expect it to have weight because it has mass and the earth is beneath it. So weight coming out from the dot. Weight. Okay, good. Next question. Any rope, strings, cables connected to the object? Well, there is one. Okay, there's one string connected to the mass. So we'll draw one rope. We'll draw one tension, sorry. Tension should be coming out from the dot, sorry. Okay, so you should expect one tension because there's one rope connected to the block, and tension we label using T. Okay, the direction of the tension should be along the rope, so you should expect either this way or this way because it's along the rope. But you know the second thing about the direction is it must be pointing away from the object. Along the rope, away from the object, and since away from the object, we remove this one because away is pointing upwards in this case. Okay, so we are done with our second question. Let's move on to the third question. Any force applied and mentioned explicitly? Well, do you see any words or any diagrams, arrows that show that there's a force being exerted explicitly? No, you see nothing being labeled over here. So in that case, there is no external force. Fourth question, is the block, the mass M over here, is it in contact with any other thing? Well, the only thing it is in contact with is the rope. And as I said just now, we have already taken into account the rope using tension already. So no other surface in contact, nothing, so no normal force. Last question, is there any rough surface? Well, if you don't even have a surface for question 4 already, definitely you have no surface for question 5. Okay, so this is our free body diagram for this object mass M over here. Well, it looks a little bit boring, right? Yes, why is it so boring? It's most probably because you pick the wrong object of interest. It's not that it's wrong, but there's a more suitable object of interest which will provide you with a better picture of the whole situation here. Okay, so the object of interest that you should pick is actually the knot in the middle over here. Okay, the knot in the middle here will be a more interesting place for us to study the forces acting on it. Okay, so let's label this one as this is a free body diagram for mass M. And now let's study the free body diagram for this knot over here. Okay, so we'll use this dot here to represent the knot. And again, I will do the same axis, X and Y. Okay, this one it's a bit, how should I say it? Whether the axis is this way or rotated won't cause a big issue over here because there's no clear tendency how the knot or the mass will move. Okay, so we have drawn our axis. Now what we need to do now is to ask ourselves the 5 questions. So the first question is does this knot have mass or not? Does this knot has mass? So the answer is no. Okay, it might be a silly question. You might think that why not? Knot is made of rope, right? Rope is made of like fibers or plastics or something. It should have mass, right? Well, that's the thing. Okay, in physics, right, there's a lot of assumption. And one of the assumption that we make when we are studying forces is we assume the mass and the rope. We assume all ropes, cables, strings, we assume them to be massless. Okay, one of the reasons why we assume it to be massless is so that our tension and will follow the Newton's third law. Okay, for now, yeah, ropes are massless, and in this case the knot here, because it's made of ropes and I say ropes is massless, therefore this knot here will be massless as well. So if it's massless, then it does not have weight. So there's no weight for this situation. Okay, so this is the first situation where you encounter there is no weight for the free body diagram. No weight because there is no mass for this knot over here. Okay, the next question, any ropes or strings or cables attached to this object of interest? Well, there is. In fact, there's a lot. There's 1, 2, 3 ropes being attached to this knot over here. So you should expect 3 tension force being labeled in this free body diagram here. Let's label them one by one. So the first one, you have one which is pointing in this direction. and the angle here should be 40 degree. Okay, then you have another one over here. Oops, this one is a bit difficult. Then this one should be 60 degree. Okay, then the last one, you have another rope pointing downwards. Okay, then this one no need to label angle. How do I know 60, 40 here? Well, it's maths. This line here, the ceiling, is parallel to the horizontal line that I draw here. And since these two lines are parallel, you know that if this is 40, this is 40. So the same idea over here, if this is parallel with this one, you know this is 60, then this is 60 degree. Okay, so now we haven't labeled any alphabets for each of the tension force. Well, if there are multiple forces of the same type, we usually label them using subscript. So in this case, I'll label things like T1, T2, or T3. So I'll label each one of them with a different subscript to indicate that they are different forces. Okay, so we have asked ourselves the second question. The third question, any force applied and mentioned explicitly? Well, there's no clear indication that there's an external force being exerted on it. You don't see any arrow, you don't see any words saying that there's a force exerted on it. So in this case, no external force. Next thing, any contact with any other thing. Is the knot in contact with any other surfaces or any other objects? Well, this knot is only connected to the strings. It's not even connected to any surfaces. So in this case, you should expect no normal force. So last question, rough surface. Well, there's no surface that you're touching. How do you get the rough surface? So if there's no contact, then therefore no rough surface. So there will be no normal force, no friction for this situation here. So no normal force, no friction, no external force. So we only have tension and we don't even have weight. So this is a complete free body diagram for the knot over here. Okay, so you can see this free body diagram is much more interesting compared to the free body diagram of the mass. So you pick the correct point, then you are able to solve the question if you have more information contained in your free body diagram. Okay, so this is how you draw a free body diagram. So a few things to take note of is a free body diagram should have a dot in the middle. That is to represent the object of interest. Then any forces that you label on the free body diagram should be coming out from the dot. Any arrows here is originating from the dot. Okay, so that's the characteristics of a free body diagram. Then for free body diagram, if you know the angle, please label the angle. That is important. And of course, if you have force of the same type, multiple forces of the same type, you can label them using subscript 1, 2, 3 situation like this. If you're wondering why is the mass over here not included in this free body diagram here, and why is the 2 string here not included in this free body diagram? Well, here's something I would like to say. If you're drawing a free body diagram for the mass, right, you only focus on what's happening in the immediate vicinity of the mass. Means right, only look around the mass only. Then you are able to draw a free body diagram for the mass. If you are drawing the free body diagram for the knot, then you only look around what happens around the knot only. You don't look at the whole situation. And you draw your free body diagram based on what you see right around the object itself. Okay, so now come back to the question, then how do you relate the mass over here to the whole situation? Because this situation here, even though it's much more interesting, it missed out the mass over here. The mass is not even mentioned over here. Okay, so we know the mass will contribute to weight, so we need to somehow relate this thing with this thing over here. Okay, so I'll just do a little quick explanation. For more detail, you need to go to Newton's third law, which we will discuss in the future videos where we talk about action-reaction pair. So basically, Newton's third law say if A exert a force on B, B will also exert the same force on A. So the two forces, we call it the action-reaction pair, and the force that A exerts on B will have the same magnitude as the force exerted by B on A. A on B will be the same as B on A. Same magnitude, but opposite direction. Okay, so the mass will be exerting a force on the knot. Okay, so this force here is relayed by this rope over here. The mass is pulling the knot through this rope over here. So this tension tree here is exerted by the mass on the knot. Okay, but at the same time, because we know that A is exerting a force on B, B will also exert a force on A. So at the same time, the knot is also pulling on the mass as well. Just that it is pulling through this tension over here. So the mass is experiencing a tension T over here, right? This tension T here is exerted by the knot on the mass over here. So this T and this T3 over here forms an action-reaction pair. This T here is exerted by the knot on mass M. This T3 here is exerted by mass M on the knot. Okay, so they form an action-reaction pair, and when they are an action-reaction pair, you know that they must be same magnitude, opposite direction. So this T over here should have the same magnitude as the T3 over here, just that they are in opposite direction. One is pointing up, one is pointing down. So what can I say? I can say that T and T3 has the same magnitude. So now no arrow, I'm just writing the magnitude. T and T3 share the same magnitude. And because we know that, now this one is Newton's third law. Because we know that this mass is not moving, so it is in equilibrium. In equilibrium, if it is in equilibrium, Newton's first law tells us that the net force acting on it should be 0. So the force acting upwards should be equal to the force acting downwards. So if T and W is the only force over here, then we know that the magnitude of T should be the same as the magnitude of W. Only they can cancel each other out to become 0 net force, and 0 net force, the object in equilibrium, not moving in this case. Okay, so we will know that since it is in equilibrium, the magnitude of T should be equal to the magnitude of W. And from there, we know that T should be equals to W. Okay, so this is how we relate the two free body diagram here together to know that actually this T3 here can be replaced also by W. Okay, after knowing this, after using Newton's third law and Newton's first law, and come to the conclusion that we can also choose to not write T3, can choose to, not a must, and you can choose to write it as W straight away. Okay, you can replace it with W, but the original one should be T3. Just that through Newton's third law, you know that T3 has the same magnitude as T, and T has the same magnitude as W. And since W is in the same direction as T3, so you know you can replace T3 with W. Okay, it's a bit complicated, but when you move on to Newton's third law and Newton's first law, slowly you'll get the idea better. Okay, so that's all I want to talk about for free body diagram. In the next few videos, we will talk about Newton's law of motion.